right? And thus this trick will help you to implement monotonic stack very, very smoothly. Now, coming on back, the problem is very simple and straightforward. We are given a positive integer nums. As you can see, we have nums. Now we have to return the number of sub-arrays of nums. Again, I will break it down. Number of sub-arrays, sub-array of an array is a portion of an array where the first and the last element of that specific sub-array which I have chosen are equal. Firstly, again, the first and the last element are equal, and also that is equal to the largest element of that specific subarray. Or indirectly, I can also say that if I take, again, let's say if this is the entire big array, if I take any portion of this array which is called as a sub array also, then the first and the last element should be same, and also that they should be the largest element of that specific subarray, which means that all the elements in between them should be less than these elements. Then I will call and I can count this as one of my good subarrays, and I can increment my answer, and thus I need to tell you how many number of such subarrays I have. For example, in this case, I can simply, let's say, again, usually how we go about these kind of problems, again, if I would have asked you, bro, you have to just let me know that what are the number of subarrays which are ending. Again, right now the condition, you have two conditions, that it should start and end at the same value, and the next condition is that all the elements in between should be smaller than that. That is one. That is these two conditions. Very brute force basic approach which would have been go on to all these subarrays and then verify this condition, which will be O of n squared to go on to all these subarrays, and then verifying the condition will be O of n again. So it will be O of n cube. But for sure, while going on to the subarrays itself, I can simply still keep on counting what is the maximum value and all that stuff. So I can improvise this O of n square into n, which is O of n cube, to O of n square also. So, but still, O of n square is still high for me. I mean, I love high things, but yeah, it is still high for me. So, what we can do? Again, we will go back to problem statement and we'll break it down. Problem asked us to say that, please bro, can you give me the number of subarrays which firstly start and end at the same value. Secondly, that in between those start and end, all the values should be small. Now, for example, let's say right now I will ignore the second condition. If I focus only on the first condition, then what could I have done? I could have, again, in all these subarray problems, I have told you the proper way to go about these problems is, again, either it is a DP or it is any subarray problem. Always go on to any of the one element. Okay, I go on to this one element and then I asked him, bro, what is your contribution? Again, if you would have also seen in this video also, I went on to one index and I asked the contribution of that one index. In this histogram problem, you went on to one index and asked the contribution of one index. So in this kind of count the contribution of the subarray, so basically when you have to do count, then you actually have to count the contribution of every index. So I will go on to this index, and then my main aim, my maqsad is, my main aim is that I have to start and end at the same value. So I will do one thing, okay, I will go on to, again, I know that I am at the specific index I, and usually I just go on in the back. Then I will look for the exact same value. Right now I can see I am standing at A. I will also look for A previously. I will look for A. Now, if I am looking for A, then, it will be very obvious that, okay, for sure, this is one subarray which I can make. Again, this is one subarray which I can make. I can make these three subarrays, and that is how I can solve it. Now, okay, simply, so what we needed? At the ith index, I need the count of all the elements which have the value A. If I know that count, I can simply add the contribution at the ith index. Okay, at the ith index, I know, okay, the count of the elements are 3. So the contribution, as in the number of subarrays which will follow the condition that will start and end at the same value will be 3, but also plus 1. Why plus 1, Aryan? Because 3 though you have seen, okay, these 3 are the ones, but 1 will also be, okay, one element is also a subarray. How? You will see by the example itself that 1 is one subarray, 4 is one subarray, 3 is one subarray, 3 is one subarray, 2 is one subarray. So you realized, okay, these were the one subarray that is also valid. Again, in this case, the 3 ending and starting both are the same values, and also there is nothing in between which is more than them. thus it is also valid. So in this example, the answer is 5, right? So okay, we also realize that okay, I can also have one subarrays, like one length subarray, that is also completely fine. Now we have solved one very big chunk. Now we have the remaining chunk, which is that in between all the elements must be small. You see that how we broke the problem down into two small problems. For one problem, we used a simple arrays concept. For next problem, we will still see, we'll see what we can use. But this is how programming works. You have to break the problem down into smaller problems. Now my problem is that, okay, number of subarrays, which let's say are again, okay, this portion is done. Now I have to just add the second thing, which is, let's say in the beginning you were at the ith index and then you were going on to the previous threes. You're saying how many threes I have, that will be my answer. But in this case, the complex thing will start coming in. What you wanted, the good subarray for you is that in between any number should not be more than 3. Okay, so I'm just scared. I'm scared of a number more than 3. So how that number will affect me? I will go and find, again, I'm not saying how I'm going and finding, but I'm scared of a number more than 3. So I will go and find for a number more than 3 in this array. Again, I am going on from left to right. So I have only visited this left portion. So I will go and find in the left portion what is location of a number more than 3. Okay, I found this location. But Aryan, how will it benefit me? It will benefit you because if this is the first location which is more than 3, Aryan, what do you mean first location? I can have many locations. I can have 8 also here. Obvious. But if you know that you will have to end at the ith index. So for you, the thing what matters is, okay, this 3 and 3 can make a subarray. This 3 and 3 can make a subarray. But this 3 and 3 will not be able to make a subarray. And again, if let's say even if I had a 3 further on, still if 8 would not have been there, still I would have not been able to make this as a subarray because of this 4 coming in picture. Thus I realized, okay, I wanted a number more than 3 and I was looking for it. I was actively looking for it. But I also realized that I want the first occurrence of a number in the left of this ith index, which is just larger than 3, which is for sure more than 3. And that too, I was doing nearest occurrence of that value, which is larger than 3, nearest occurrence of that value in the left of this ith index. Because I will actively go and look for this higher value. Because what if this 4 would have been here, then I would have not been able to make this as a subarray. Nah, I will only be able to make this. So I'm actively looking for any number which is more than 3, and I will go and look from the left onwards. But Aryan, if you will go and look actively from the left, as in you will go from the ith index and you will keep on going back, then it will take O of n time for one index, and you have n index, so it will take O of n square time. How it will help you? You have to do it in O of n time. Yeah, true. Do you think any algorithm? Can you remember of any algorithm which you have studied? For sure. Nearest to an element which is just larger than him. In this video, I have told you 4 wordings that if you hear this wording ever, you know that you will apply monotonic stack. You have to go and find the nearest element to the left that is larger than nums of I. And that nearest will give me the location, okay, the location of this 4. And thus I will be very safe. That okay, after this 4 only I will take, okay, before this 4 any of the 3 which is coming, I will ignore them or I will discard them. So now my main task becomes that okay, I will use a monotonic stack to know the nearest leftmost occurrence of a just higher element. But you know that usually in these kind of problems it is hard. It is easy to think it will be applied, but it is kind of tricky to implement it. In this video itself, I told you a trick how to implement it and how to know what to implement, because we know that okay, it is monotonic. We never know how the stack will look like. It may be increasing, it may be decreasing. So we will not take the load of this. We will just simply go and do whatsoever the problem was saying us to do. What he was saying, that if we are at 3, we need to know the nearest occurrence of an element higher than 3, and that too in O of 1 time. So if, again, for sure, we'll use a stack because it is monotonic stack. So if, let's say, in my stack, I had 4, 3, 2, and so on and so forth. I had 4, 3, 2. Now I am at the ith index. So I will look for, basically I'm looking for 4. And that too I want in O of 1 time. So anything post 4 I should remove. So basically this 2 and this 3 I am removing so that I am able to grab this 4 in O of 1 time. So what is happening? You firstly grab this ID, which is at the top. So you grab the ID at the top, and then what you are removing? You are removing again nums of ID if it is less, because if you remember it was a 3. So if nums of ID, which is 2 right now, and nums of I is 3. If nums of ID is less, and you can also see 3 also I removed. If nums of ID is less or equal to your nums of I, then you will remove that from the stack. So you will remove this, and thus you would be getting your top element as 4. And for sure, when you have 4, you know that, again, right now in this, I'm showing you the values which I'm putting in the stack. But ideally, in all these cases, you put in the indexes in the stack so as to easily retrieve and modify the values. But make sure that this condition you are able to figure out by just seeing that you wanted 4 in O of 1 time. So anything after this, you will remove. What you're removing? You're removing anything which is less than nums of I. Thus, you can simply solve it. This is a trick which I told you just to do quickly, super fast. Now, coming on back, that it is exact same. Again, it is the exact same code which we saw in this video also. Exact same code. Again, I'll show you a quick thing that what we do. Okay, we have to initialize our ID by -1 because, okay, what if the leftmost is -1? Like nothing. I have no one in the leftmost, so it will be -1 by default. And thus, if I am validating this condition, so I will just keep on popping from the stack. As in, if I will pop, I will update my ID also, and then ultimately I should also push the current index I in the stack also, and then I will update my left of I with the ID, saying that for this I index, nearest left index, which is just higher than me, is at the index 9. So I'll just simply update. Left of 16 is 9. Cool. Now with this, you know that, okay, you will be knowing the left of every index in O of n time, total O of n time. But still the problem is not solved. Aryan, but it is solved, right? I know this index. I know all the occurrences of the 3. I will just simply remove the occurrences of 3. Are you sure that you know it? Because, okay, all the occurrences of 3. Earlier, my 3 was at this index. The occurrences of 3 were 7, 11, and 13. 7, 11, 13. So when you were at I, you were taking all the previous occurrences. So you were taking the count earlier. You were taking the count, which is 3. And for sure, make sure to plus add a 1. 1 for myself itself, which means me to me. But right now, because of the leftmost occurrence, which I have calculated by using Monotonic Stack right now, I've got a 9. Which means any index which is lesser than 9, I should ignore. So earlier, I had the size of my map. Again, I will store, okay, for the element 3, which means map of my element, which is 3, I will be storing the indexes for it. Indexes as in, okay, I have indexes of 7, index of 11, index of 13, and so on and so forth. So I will be storing the indexes for every corresponding element because I am concerned about the pair for making a pair and the same value. So if I will make this, then, okay, it seems nice that Aryan, it is simply, I will do a what? I will do a binary search. I will simply go and do a binary search in this vector and I can simply go and find my answer. I will say you are absolutely right and it will work also. But, okay, again, you will see that maybe you might end up thinking, Aryan, maybe I'm not able to do a binary search and stuff. Maybe it is not possible. Maybe it is possible. But I'll say, bro, you don't have to worry at all because these indexes will always be sorted. Because you remember, you are going on from left to right. So these left to right, which means indexing is from left to right. So this array will always be sorted. So ideally, you can simply take an unordered map from int to a vector of int. But just to add on, maybe in worst case that you encountered a problem in which, let's say, your this entire portion would not have been sorted, and you were pushing an index which is arbitrary, but still you had to go and find that, bro, what is the location of this specific 9, because anything which is smaller than 9, I will remove it. Then you would have used a policy based data structure. But a quick disclaimer, it can also be solved without using a policy based data structure, because my indexes array will always be sorted, because I will be pushing in the elements in the 0 to n minus 1, I will be pushing in this order itself, so this will always be sorted. So ideally in this case, I can just simply go and check, okay, what is the lower bound or upper bound of 9? Both will work because indexing will never overlap. So what is the lower bound of 9 or upper bound of 9? That will give me a location, and anything post that location is a good location. Before this location, I will ignore that. So again, as I told you, that you can also use the PBDS, but the benefit of this, why I'm teaching this right now, PBDS, is that maybe, as we had already seen in the previous cases, maybe that your or like this indexing which you have been which you have put in, maybe you are not dealing with the indexes, maybe you would have been dealing with the values directly, then this policy based data structure would have been very beneficial. But say in this case, you can also apply vector, simple binary search, simple upper bound and lower bound. Now you will simply go and search for this 9, and when this 9 is there, you can simply say that, bro, anything which is smaller than 9, like index 9, and say I'll simply ignore it. So I will have the count. Simple. It is very easy to get the count itself, and thus I will be knowing that whatsoever I had the entire size of the vector, which is map of 3 dot size, and then when I have got the upper bound or the lower bound, he will just point me here. Then I would be knowing that this is the count of the elements which is lesser than my 9. And thus I will subtract from my map.size. And the same way I can implement that with my PBDS also, because PBDS has a order of key which says number of elements strictly less than my k. So I can also use my PBDS to find this number of elements strictly less than my 9. Cool. Now I'll show you the code. It's pretty simple. Again, I'm telling you that we can also solve it by simple as in simple binary search. The only reason I told you PBDS is, what if you would have been dealing with the nums, which means element itself rather than indexes? Then it is highly beneficial for you to know that you can also use the path of PBDS. So in the very beginning, I had larger left, which means, okay, just left, what is a larger element than me? I will simply have a stack, push the -1 in the very beginning. I'll go on to all the elements, get the top. If it is not -1 element, I'll get the element, and then if it is less than or equal to my nums of I have to pop it out, and then I will keep on popping out until it is less than equal to. As soon as it is more, I know that this is my Bapu, which means that firstly I will push the current index, and I know that this is my Bapu. Now I'll go on and find the answer. Here I simply took a integer and I took a ordered set. Again, this ordered set is actually my PBDS, but I told you that you can also take a simple vector, because this thing will already be sorted, because you are pushing the indexes. Because what you're doing, you are saying that pushing the insert of I is always increasing, so you're pushing in the increasing order itself. That's the reason I told you that you can also use vector, simple vector here. It should be much better. Now element, I went on the elements. I went on and checked for the nearest largest element ID by using my largest left, this array itself. Then I went on and counted what are all the elements. Again, this element map of element dot size will give me the total count of indexes which has the value element. I'll subtract all of them which has the index which is less than my this index, which is nearest larger element index, which indirectly I'm trying to say which has the index of, let's say, 4, right? Which has the index of 4. So I'll just remove all the elements which have the index lesser than 4. I will simply remove them from my count, which is the total count of all the elements which I had, and thus I will be getting the desired count, which will have no larger element in between, and thus I can simply add the contribution of that count. +1, remembered, my to myself, this is the answer, +1, and simply keep on inserting the index itself in your map, unordered map. Thus you will be using a O of n log n time, no matter what, if you use your PBDS, or if you use your vector, or if you use your unordered map or set. And space will be O of n, because you will be storing these elements in your data structure. Cool. That is how you simply solve it. Bye bye, take care. Again, I try to teach everything because again, this is one contest, but the contest varies. Problem can be switched. So you should never be confused, okay, what to apply and what to apply. So make sure you know the things and how to apply these concepts. Bye bye.